discuss about 8051 microcontrollers. But before going to 8051, let us discuss what is microcontrollers and what is the main difference between a controller and a processor. Now here, as the name micro indicates small in size and controller indicates a device which is capable of controlling the functionality of a system or controlling the functionality of a machine. For example, if I take the example as washing machine, the main functionality of washing machine is just to wash the clothes, but we are controlling that machine with the help of one IC, and that IC is called as a controller. Generally, these microcontrollers are used in most of the electronic gadgets where we require to control the functionality of any kind of system. Okay, now let us see what is a microprocessor initially. So what is a microprocessor? It is also called as general purpose microprocessor. Why? Because we can use these processors in any kind of application, and this is used in CPU for computers and no RAM ROM, so it doesn't have any external peripherals. So we have to connect the external peripherals to make it as a full computer. So if I want to make a processor as a computer, then I have to connect RAM, ROM, input output port, timer, serial communication port, and many of the peripherals that should be connected to this CPU. Then this particular block, this complete block will become a complete computer. Okay, and this processor can be used in any kind of application, so that is why it is called as general purpose microprocessor. And this complete block represents how to build a computer with the help of a processor and some peripherals. Okay, and the examples are Intel 8086 architecture and then Motorola's 680 into 0 architecture. Now let us see what is a microcontroller. So a small computer on chip RAM, ROM, input output ports. So here this microcontroller is also called as a application specific device, and it is also called as system on chip. So in order to make a computer from a processor, we have to add all these peripherals, but all these peripherals as well as the processor will be embedded on a single chip. So that is why it is called as a system on a single chip, and this is mainly used for a specific application. So that is why it is called as a application specific device. For example, if I'm using this microcontroller for controlling the functionality of a washing machine, so I'm going to write a program in such a way that this controller is going to control only the washing machine functionality. Now, in order to use, if I use the same IC, that is same microcontroller IC in some other application like microwave oven, then it doesn't work. I can use, but the thing is I have to modify the contents which are written already inside this ROM. Okay, so modification is required. Without modification, I cannot use the same IC in some other applications. So that is why this is called as application specific device. And examples are Motorola 6811, Intel 8051, and then Xilox Z8 and PIC16X, and there are many other controllers available in the market from the different manufacturers. Okay, so that is why it is called as a application specific device, as well as it is also called as system on chip. So all the peripherals will be inside this single chip. Now let us see what is the main difference between a processor and a controller. So CPU standalone, RAM, ROM, input output, timer are separate. So we have to connect the peripherals externally to the processor, but whereas when it comes to microcontroller, all these peripherals will be inside a single chip. Okay, so designer can decide on the amount of ROM and RAM and input output ports. So here if I have a processor, I want to connect any kind of memory like RAM and ROM, then I can connect that is any amount of memory. Okay, but whereas here fixed amount of on-chip ROM and RAM, input output ports. So there are fixed amount of ROM as well as RAM as well as some input output ports, and all the peripherals which are inside this microcontroller are fixed, so we cannot change them. And it is called as general purpose, as I told you that it can be used in any kind of application, but it is called as application specific. Why? Because if we are designing a controller for specific application, that cannot be used for the other application without modification. Okay, that modification is possible because of the present day ICs. Why? Because the present day ICs are included with flash ROMs, and it takes larger area. So as we have to connect all the peripherals, so it is going to take a large area. But whereas coming to the microcontroller, all those are embedded on a single chip, so that is why it takes a small area, and for applications in which cost, power and space are critical. So we are going to use these microcontrollers where cost, power and space are some critical requirements for us. Now let us see what is a system bus. A system bus is a set of wires that interconnects all the components of a computer. So bus is nothing but a set of wires. So here system bus is again a set of wires which is going to interconnect all the major peripherals of the computer. Okay, so with the help of this system bus, all the peripherals along with the processor is going to communicate with each other. Okay, and this system bus internally has three buses, that is address bus, data bus and control bus. So address bus is unidirectional, which is from the processor to the peripherals, and data bus is bidirectional. Why? Because data can be transmitted by the processor as well as it can be received from the peripherals. And control bus, it is also bidirectional, and the direction of signal from the processor to the peripherals will be called as a control signal, and the direction of the same bus from the peripherals to the processor will be called as a acknowledged signals. Okay, so here address bus is mainly used for carrying the address from the processor to the peripherals, and data bus for carrying the data from the processor to the peripherals as well as from the peripherals to the processor, and control bus is used for carrying the control signals. For example, assuming that there is one processor which is connected to three input output devices. Now it has to communicate with the first input output device. So initially the processor is going to send the address bus, that is going to send the address through this address bus, so that one of the peripheral will be selected, and then it is going to send the control signal whether it wants to read or write the information from the peripheral. After sending the control signal, then it will send the data from the data bus. So this is what actually happens with this system bus. Okay, so system bus is mainly used for connecting all the major components of the computer. Now let us start 8051 microcontroller. The manufacturer of this 8051 controller is Intel, and it's one of the famous controller which is mostly used in all the applications. It's frankly speaking, it is not a controller, it is an architecture. So based on this architecture, many of the controllers are designed. Okay, so let us see that. Initially let us see the important features of this 8051 controller. As I told you that it has internally RAM and ROM, so there would be a fixed amount of RAM as well as fixed amount of ROM. Okay, so 4 kilobytes of internal ROM, 128 bytes of internal RAM, 4 8-bit input output ports. So there are totally 4 8-bit input output ports. It means I can connect a total number of 32 input outputs. Okay, and then 2 16-bit timers. So we have 2 16-bit timers, and we'll discuss about these timers and counters in the later sessions. And one serial interface which is mainly used for communication between the processor and the serial devices like mouse, keyboard, and then 6 interrupts. So there are totally 6 interrupt sources. Okay, so later in the later sessions we are going to discuss about these timers, serial communication as well as the interrupts. Okay, now let us see the pin diagram. If we know the pin diagram, then I can connect any kind of peripherals to the controller. If I know the functionality of each and every pin, then I can connect some input or output devices to the controller based on the pin functionality. Okay, so let us see, let us start our discussion with pin diagram. So this completely shows a 40 pin diagram of 8051, where you can see there are totally 40 pins, and it is called as DIP. DIP is nothing but dual inline package. Okay, this kind of package is called as DIP dual inline package. As you can see here, it totally has 40 pins. Out of these 40 pins, 32 pins are reserved for input output pins along with some other functionality, and remaining 8 pins are going to function something like VCC, reset, ground. Okay, so let us see initially about the remaining 8 pins, and then later on we'll discuss about these 32 pins. Okay, so here reset, Xtal2 and Xtal1, VCC, EA bar by VPP, ALE by program bar, PSEN bar, and then ground. Now all these 8 pins will be providing us some different functionalities. So let us see what are those functionalities. Now here, so VCC is a 40th pin, and it is mainly used for giving the supply voltage to the 8051 controller. As we know that if it is an electronic device, if it is a digital device, then definitely we have to give an DC supply. Okay, and here this controller runs with a maximum voltage of 5 volts. So if this voltage is exceeded, that is more than 5 volts is given to the controller, then the controller gets damaged. So we have to give a voltage of only 5 volts. And then ground, as you can see, it is a pin 20, so which is mainly used for directing the higher currents or voltages towards the ground. And then XL1 and XL2, these are called as crystal pins. Okay, and these are mainly used for connecting a crystal oscillator to the microcontroller. What is the need of an oscillator? Generally, all the electronic devices require the clock signal. Why? Because if it is involved with memory components, then definitely it requires a clock signal. Why? Because all the memory components or memory peripherals will be working only on the clock signal that it is going to receive. So in order to generate a continuous clock signal, we require an oscillator. Okay, and oscillator internally contains one inverting amplifier along with some feedback element. Okay, and it has to satisfy the Bark-Hassan criteria so that we can say that that it is an oscillator. Okay, now here we can design that feedback element with the help of RLC components. But if we are going with RLC components, then there are some drawbacks associated with those components. So that is why we are going with one more component, that is crystal. So we are designing the feedback element with the help of this crystal. Okay, let us see how to design that. So XL1 and XL2 pins, 19 and 18, these two pins provide external clock, as I told you that. And then way 1, so here we can connect this oscillator in 2 ways. The one is by using the crystal oscillator, and the other one is by using the TTL oscillator. It means some external oscillator which is directly given as a input signal. Okay, now let us see how to do that. And see, internally in the controller we have an inverting amplifier. So as we have an inverting amplifier, then we require to add only the feedback element. So let us see how to design that feedback element. Now this is the first way where I am going to use the crystal. Okay, so here XL2 and XL1, these are the 2 pins to which one crystal is connected. Along with the crystal, 2 capacitors are connected, and the other end of the capacitors are connected to the ground. Now these capacitors will be giving us the AC input signal, that is the transient response, and then this oscillator is going to work with the help of this transient response. Okay, so this is how we are going to give the clock signal to the microcontroller. So internally we have an inverting amplifier. So this is nothing but the feedback element. Okay, and the crystal which we are going to use in case of 8051 controller is 11.0592 megahertz. Because we are using the specific 11.0592 because in order to go with serial communication, we definitely have to use 11.0592 megahertz. It supports, this crystal is going to support the serial communication. Okay, now let us see the other way how to connect the same oscillator signal to the microcontroller. So here crystal 2 is not connected, that is crystal 2 pin is not connected, but whereas XL1 pin is connected to the external oscillator signal. So directly we are giving the signal to this particular pin. Okay, now here 12 clock cycles is a machine cycle. So inside this 8051 controller, 12 clock cycles is nothing but a machine cycle. So here the machine cycle or clock cycles, the number of clock cycles depends on the controller which we are using or processor which we are using. Now when it comes to 8051, 12 clock cycles is nothing but a single machine cycle. Okay, now let us see what is this machine cycle. So machine cycle, time taken by the processor to execute an instruction. So there might be any number of instructions inside the controller which is going to support any number of instructions, and those instructions might some might be of 1 byte, some might be of 2 byte, and some might be of 3 byte. Okay, so here the time taken by the processor to execute an instruction, here instruction is nothing but 1 byte instruction. Okay, so here the time taken by the processor to execute a 1 byte instruction is nothing but a machine cycle. Okay, now here this machine cycle is again divided into 2 more cycles, that is instruction cycle and execute cycle. Okay, let us see what is that instruction cycle and execute cycle. As we know that all the instructions are present inside the memory, so the processor has to fetch those instructions from the memory. So here during this instruction cycle, fetch and decode operations will be performed by the processor. Okay, so during that time the processor is going to fetch the instruction from the memory, and then it is going to decode that instruction to the understandable language of the processor. Why? Because the instructions which user is going to write, all those instructions will be in high level language. Okay, so it is going to decode those instructions to the language which is understandable by the processor. Okay, then execute cycle. So during this period it performs the execution as well as writes the result to the memory again. Okay, so this is what instruction cycle and memory cycle. Now let us see the pins of 8051. As you can see, there is one pin which is reset. This is the 9th pin. It is similar to the restart pin which we have for every kind of computers. So restart is the switch which is mainly used for restarting or rebooting the computer. So in the same way, reset is the pin which is mainly used for resetting the controller. What happens when you reset the controller? Whenever we reset the controller, then all the memory or all the registers inside the controller will be initialized to 0, and or else will be initialized to a defined value except some registers. Okay, so here it is a 9th pin and input pin. It is an input pin and it is also called as active high pin. There are two kinds of pins. One is active high and the other one is active low. Okay, so if we are giving a logic high to an active high, then it gets enabled. If you are giving a logic 0 to active low, then it gets enabled. Okay, now here the high pulse must be high at least 2 machine cycles. So here we have to give a logic high signal on this reset pin for 2 machine cycles, then only the controller gets into the reset state completely. If you are giving less than these 2 machine cycles, then it will not work properly. Okay, so that is why we have to maintain a logic high pulse on this reset pin for a period of 2 machine cycles. Now what is the period of a single machine cycle? That we have to calculate. That is, we have 12 clock cycles is nothing but a machine cycle. The frequency of a single clock cycle is 11.0592. So we get something like microseconds. Okay, microseconds in this machine cycles. Now we can design a circuit for this reset pin. One of the circuit is called as power on reset. So upon applying a high pulse to the reset, the microcontroller will reset and all values in registers will be lost. So as I told you that whenever you apply a logic high pulse on this reset pin, then all the registers inside the controller will be initialized to some defined value. Okay, those defined value might be 0 for some registers and those defined value might be something like FF for some other registers. Okay, let us see how to design this power on reset circuit. Why? Because it is difficult for us to monitor these 2 machine cycles. It is difficult for us to give a logic high pulse manually for a period of 2 machine cycles. So that is why we'll design a circuit which is going to take care of this particular time duration, that is 2 machine cycles. Now this is what the circuit, this is how the circuit looks like, and this is the controller and this is the reset pin, to which one capacitor and resistor are connected, and one end of the capacitor is connected to positive 5 volts. Now here this is called as power on reset. Why? Because whenever you give the power, whenever you give the supply voltage to the controller, then the controller will be in a reset state. Okay, let us see how it happens. So as soon as you give the 5 volt supply to this capacitor, then it works as a battery. Okay, therefore this reset pin will be holding a logic high pulse. Okay, and it will be holding this logic high pulse until this capacitor gets completely charged to this VCC. So as soon as this capacitor gets completely charged to VCC, then it will not allow any other supply to cross this capacitor. Therefore this reset is logically connected to ground, which is nothing but a 0 is applied over here. In case of digital, logic 1 is nothing but the supply voltage and logic 0 is nothing but the ground voltage. Okay, and we have to select this capacitor as well as the resistor values in such a way to get only the time duration of only 2 machine cycles. Okay, so that is why this particular circuit is called as power on reset. For example, assume that we are working on the controller and we want to reset the controller in the middle of some application. So here if we if you connect this supply and if you remove the supply, if you again connect the supply, then then the controller gets reset. But this is not required for us, so that is why we are going with a switch. This is called as power on reset with manual switch. Okay, so initially without this switch it works as power on reset, but in the middle of the application, if you want to reset the controller, then this switch must be closed. So as soon as you close the switch, then the supply voltage will be reaching to this reset pin. Okay, so this is how you are going to reset the controller with the help of this reset pin. Now these are all the values, or these are all the registers which are defined to some specific values whenever the processor is in reset state. That is, program counter will be initialized to 0, accumulator will be initialized to 0, B register would be initialized to 0, program status word will be initialized to 0, stack pointer will be holding 7, and then data pointer will be holding zeros, and all the locations inside the RAM will be filled up with zeros. Now let us see one more pin, that is PSEN, which is called as program store enable, and this is an output signal from the controller, and it is an active low pin, which is nothing but a logic 0 is supplied to activate something. Okay, and this pin should be connected to OE pin of the ROM. Okay, as we know that whenever a logic 0 is received by this OE pin, then the peripheral can read the data from the then the processor can read the data from the peripheral. So that is why this PSEN is connected to OE pin of the ROM. And then we have one more, that is external access, which is mainly used for enabling the external access. So here it is an active high pin, so a logic 1 to be connected to this particular pin. Okay, and for example, assume that we have in case of 8051 we have only 4 kilobytes of ROM. Assuming that we have written one application code whose size is more than 4 KB, then I cannot store some of the code inside the inside my internal memory and some of my code in the external memory. So in what I'm going to do is I'm going to connect one external peripheral memory device, and then I'm going to store my application code inside that memory. Now here the controller doesn't here the controller always fetches the instructions only from the internal memory. Why? Because this pin is initially connected to ground. So if you are connecting this particular pin to logic high, then the controller knows the information that our application code is present inside the external memory. Now it is going to access the code from the external memory. Okay, so there is no on-chip ROM for 8031, 8032. So in those cases we will be using this EA pin, and EA pin is connected to ground to indicate the code is stored externally. PSEN bar, ALE are used for external ROM. For 8051, EA pin is connected to VCC. Okay, now here ALE, there is one more pin, that is ALE, address latch enable, and here this particular pin is going to differentiate port 0, which means port 0 will be called as multiplex lines. So it is going to differentiate the address and the data information which is carried by port 0. Okay, so we'll see this later on when we discuss about this port 0. Okay, so that completes the 8 pins, okay, other than the port pins. Okay, now let us see the port pins. Port 0, which is of totally 8 pins, as you can see here, port 0.0 to 0.7. Now these port pins, all these port pins are called as multiple functionality pins. Why? Because we can use these pins for more than one function. It means I can use the same pins to act as input, I can use the same pins to act as output, and I can also use these pins as multiplex lines. It means here AD represent two kinds of information, that is address and data. Now these lines are capable of carrying address as well as they are capable of carrying data information. So that is why they are called as multiplexed lines. Okay, and here this is going to carry the lower byte address, that is A0 to A7. Now let us see the next port, that is port 1. It is again having 8 pins, that is P1.0 to P1.7, and these are also called as multiple functionality ports. Why? Because these pins can be used as input as well as output. Okay, now we have port 2. Port 2 again it is having totally 8 pins, P2.0 to 2.7, and here you can see that it is going to carry the address information, that is from A8 to A15, which is nothing but the higher byte address. Okay, so I can use these pins as input, I can use these pins as output, I can also use the same pins as address lines, that is higher byte address lines. Okay, that and these address lines and data lines are mainly used whenever we connect some external memory or external peripheral. Okay, next we have port 3. It is again having 8 pins, P3.0 to 3.7, and apart from these input output functionality, now it is going to provide some special functions like RxD, TxD, and these two pins or these two functionalities are mainly used in case of serial communication, so we'll discuss it later. And then INT 0 bar and INT 1 bar, these are active low pins and these are interrupt pins, and we'll discuss about these pins later during the interrupts. And T0 and T1, these are timer pins, and we'll discuss them when we discuss about the timers. And then we have WR bar and RD bar, which are mainly used for connecting some external RAM. Okay, so here WR bar is connected to WR bar pin of RAM, external RAM, and then RD bar is connected to OE bar pin of external RAM. Okay, so this is how we are going to use all these port pins. So if I want to use any of these port pins to act as output, then we have to write some logical values into those port pins. Why? Because each and every port is provided with 8-bit flip-flops or 8-bit register. Okay, so every pin is associated with a single flip-flop, therefore a complete port is associated with a register. So if I want to access any of these port to act as output, then those port registers should be initialized with zeros. If I want to access any of these port pins to act as input, then those registers should be initialized with logic 1s. And the same registers are going to hold the data when we want to transmit or when we want to receive from the external peripherals. So in the next coming session, we'll discuss about timers. Thank you.